In this video, I'll be talking about the application of Gauss law. So the first application will use Gauss law to find out the electric field due to a charged hollow spherical cell. Okay, it's a charged hollow spherical cell. So this is a charged hollow spherical cell. Okay, it's a sphere but nothing inside, it's a hollow. And we assume the total charge that is uniformly distributed over this spherical cell is Q. That's the total charge. And we are interested in finding out the electric field at a point P, which is outside. First we'll talk about what is the electric field outside, and then we'll talk about what is the electric field inside. So let's first talk about what is the electric field due to this hollow charged spherical cell at a point P, which is outside or at a distance r. We assume the radius of this sphere or the hollow spherical cell is r. The capital R is the radius. Okay. Now what we're going to do, we're going to draw an imaginary Gaussian surface. As we are interested in finding out the electric field at this point, what we're going to do, we'll draw an imaginary Gaussian surface. Let me do it this way. Okay. And then this is the center of both is exactly the same. I have drawn here, so let's focus onto this one. So this is our charged hollow spherical cell, and we are interested in finding out the electric field which is outside. The radius of the charged hollow spherical cell is r, and we are interested in finding out the electric field at point P, which is at a distance r. As this charge is positive charge, the electric field is outside, is radially outward, because the electric field is always outward for a positive charge. Okay, nice. So now what you have to look at it, if I just take at this point the area vector is this way and the electric field is also this way. So both area vector and the electric field are in the same direction. It doesn't matter where you take it. That's the reason of choosing a spherical Gaussian surface. You could have chosen this Gaussian surface too, but the problem with choosing this kind of Gaussian surface is because you do not know the area will be this way and the electric field is this way. So you have to find out the angle. Then it will be a lot more complicated. And that's the reason we're just choosing a symmetric Gaussian surface just to make life easier. If we just choose a spherically symmetric surface, then it is a lot easier to integrate rather than choosing an arbitrary Gaussian surface. Okay, so again, at any point the area vector and the electric field are in the same direction, so the angle is exactly equal to 0 at all points. It doesn't matter where you take it, the angle between electric field and the area is 0. Okay, so what does the Gauss law tell you? The Gauss law tell you the total electric flux passing through a closed surface is equal to Q enclosed divided by the permittivity of the medium, or epsilon naught. This is the Gauss law. Now our goal is to integrate this integration. Again, remember what is E? E is the electric field and dA is the elementary area. Okay, so now if you look at this point, the electric field at all points is exactly the same. It doesn't matter where you take it, just by symmetry the electric field at any point is exactly the same. So E is a constant quantity because it is exactly the same distance on the sphere. So this is a constant, and the angle between E vector and the area vector is 0 degree, and cosine 0 degree is 1. So E dot A vector in this case is simply given by E A cosine theta, and cosine theta is 0. So E D and we just have the cosine theta is 1. Okay, so now let's come back here. So in this case, as you see now, E vector dot dA vector is equal to, E is a constant, so I'm just taking constant, and then we have a dA vector, dA, and this dA, what does this dA means? This is the total surface area of the Gaussian surface. That's the total surface area, and this total surface area is now exactly equal to 4 pi r square. So that's the reason here I have written 4 pi r square. And if you look at the Gaussian and the Gauss law, it says the Q enclosed, the total charged enclosed by this Gaussian surface is the charge of the charge ring, which is exactly equal to Q. So this is the charge enclosed and divided by the permittivity of the medium. Then we can solve for electric field, and the electric field will be Q over 4 pi epsilon naught r square. And we know that 1 over 4 pi epsilon naught we denote by another constant that is called K. And the value of K is 9 times 10 to the 9 Newton meter square per coulomb square. That is a constant for air medium. If you have another medium, then it will be the different. Okay. So what does this equation look like? This equation is exactly looks like the electric field due to a point charge. Due to if you look any point charge, that's what the electric field is. For any point charge, what is the value of the electric field? KQ over r square. So even for the hollow spherical shell, we get exactly the same equation. That means if you for any point outside, what does it look like? The entire charge is concentrated at the center of the spherical shell. That's how it looks like. Okay, it does it. So if you have this point, then how do you calculate the electric field? K, the total charge, divided by r square, and the r will be this distance. So for any point outside, the entire charge seems to be concentrated at the center of the sphere. Now let's talk about the case 2. And the case 2 is, what if the point lies inside the hollow sphere? Okay, so now let's go back here. So instead of so this is our charge. Now the point is somewhere here inside the hollow spherical shell. Now we will find out what is the total electric field at this point. Okay, so again, what are we going to do? We're going to use the Gauss law. We're going to apply the Gauss law. So for this one, we again choose a Gaussian surface, again a spherical Gaussian surface. Here we have created a Gaussian surface here, which is at a distance r. The radius of the Gaussian surface is r. Okay, so now let's find out what is the electric field, this one, by application of Gauss law. So what does the Gauss law tell you? The Gauss law tell you the total flux is given by Q enclosed over epsilon naught. That's the Gauss law tells you. And again, E by symmetry, if you have any electric field, it will be the constant at any points just because of the symmetry. And 4 pi r square is the surface area of the Gaussian surface. But now what is the Q enclosed? If you just take this Gaussian surface, how much charge is enclosed by this Gaussian surface? There is no charge at all, because the charges are outside. There is no any charges inside the Gaussian surface. So the Q enclosed in this case is 0. So what does that mean? That means at any points on the Gaussian surface, the total electric field is entirely 0. That means at this point the electric field will be 0. At this point the electric field is 0. It doesn't matter where you are at, the total electric field is exactly equal to 0. Okay? So now let me tell you some beauty about the electric the hollow spherical cell. As there is no any electric field inside, it is perfectly safe to stay inside a car during a thunderstorm. So when you see the lightning, when you see a thunderstorm, you stay inside the car because a car is assumed to be hollow, the box, so there is no electric field inside, so you won't feel any electric shock if you stay inside a car. Okay, so this is the reason, because electric field inside any hollow sphere or any hollow thing, the electric field inside it is always equal to 0. Now if I plot the graph of the electric field due to a hollow sphere cell, how does it look like? As you know, the inside the electric field is exactly equal to 0, and outside the electric field varies as 1 over r squared. So inside it is 0 and outside it just varies as this one, and the electric field is maximum on the surface. Okay, so this is it for the Gauss law, the application of the Gauss law, in which case we talked about how to find the electric field due to